and this be the parametric description of the frame. Thus the following differential equation defines the shape of the soft film: del square f by del x square plus del square f by del y square equal to 0 inside the region, and along the boundary it is f of x and y, that is ultimately being a function of t. So this is the Laplace's equation with Dirichlet boundary conditions given there. So several identities can be derived for operators of gradient, divergence, rotor or curl, and Laplacian. Now to solve a partial differential equation, there is a method that is most frequently used when we solve a partial differential equation: wave equation, heat equation, Laplace equation, and that is method of separation of variables. This is similar to the method of separation of variable in case of the ordinary differential equations. There, if you have a first order linear differential equation, and you can write that equation in the form all the terms containing x with dx equal to all the terms containing y variable with respect to dy, then that is called the variable separable form. Similar thing is takes the form here. So method of separation of variables is often used to determine the solution of a linear partial differential equation. Now first we consider a problem. Suppose that a slab depending indefinitely in the y and z directions at any initial temperature T1 has its two faces suddenly cooled to temperature T0. Now what is relation between temperature, time after quenching, and position within this slab? So this is described by a linear PDE, and we are going to solve this by method of separation of variable. So as shown in the figure, the condition in this problem: since the solid extends indefinitely in y and z direction, heat flows only in the x direction. The heat conduction equation and boundary conditions are: the heat equation in this only one direction it is considered, so only in x direction it is there, so one dimensional heat equation is considered here with these four boundary conditions: del T by del T, capital T is temperature, small t is time, and x is the showing the x direction. So del T by, so two independent variables here are considered, x and t, the space coordinate x and the time coordinate t, and capital T is the temperature at position x at time t, describing by this differential equation, one dimensional heat equation. Del T by del T equal to alpha into del square T by del x square, and the initial conditions are: temperature is T1 at when t equal to 0, that is initially for x greater than 0. Temperature is T0 when time is at any time at infinite time when x is greater than 0. Temperature is T0 at x equal to 0 and t greater than 0, and temperature is T0 at x equal to 2r and at any time. So the differential equation del T by del T equal to alpha del square T by del x square, by the this equation is transferred to another coordinates by the transformation theta equal to t minus t0 by t1 minus t0 for some simplification, and it takes the form del theta by del t equal to alpha into del square theta by del x square. So this transformation simplifies the boundary conditions that are going to be used. So the conditions, the given boundary conditions in terms of T, temperature, capital T, now under the given transformation takes this form: theta is 1 at t equal to 0, x greater than 0, theta is 0 at t equal to infinity and x is greater than 0, theta equal to 0 when x equal to 0, t greater than 0, and theta equal to 0 at x equal to 2r and t greater than 0. Now in method of separation of variable, when applied for a linear partial differential equation, we assume the solution, and solution is assumed in terms of the product of functions, and each function in this product is function of the single independent variable. Here theta is in the differential equation you can see that we are going to solve the differential equation is del theta by del t equal to alpha into del square theta by del x square. So theta is depending on two independent variables x and t, and so the solution assumed is a product of two functions, a function of x only and a function of t only. So theta is f is a function of x only and into g a function of t only. So with this now we find the derivative of this expression, the assumed solution, which are needed in the given differential equation to replace. So del theta by del t, that is fx into g dash t. So del by del t of gt and d by dt of gt are the same because g is function of a single variable, single independent variable. Okay. In case of single independent variable, the partial derivative of the function and the ordinary derivative of the function are the same. And next is del square x by del square theta by del x square, that is f double dash x into gt. So we put this into the given partial differential equation and we have fx into g dash t equal to alpha into f double dash x into gt. Now we can separate the variables. So fx into g dash t is equal to alpha into f double dash x into gt. We can write this as f double dash x upon fx. We collect the functions of x, derivative and functions of x on one side, and on the other side the derivative of with respect to t and the function of t. So it is f double dash x upon fx, that will be equal to g dash t upon alpha into gt. And you can see both the left hand side is function of x only, right hand side is function of t only. That is the some problem there in the notation in the slide, and that is assumed to be arbitrary constant lambda. Here minus lambda is considered so that we get plus sign in the resultant equations. So f double dash x by fx is equal to minus lambda and g dash t upon alpha gt, that is equal to minus lambda. This gives us, these two expressions gives us, these two equations gives us two ordinary differential equations. First is f double dash x plus lambda into fx equal to 0, that is second order derivative of f with respect to x, and it is with respect to x and function is of only one variable x, so that is ordinary derivative of second order, plus lambda into fx equal to 0, and g dash t plus lambda into alpha into gt equal to 0. So second equation is first order ordinary differential equation, first equation is second order ordinary differential equation. Now you know how to solve an ordinary differential equation. Okay, these are homogeneous differential equations, ordinary homogeneous differential equations, and their solution, their general solution is given by simply finding their complementary function. Their particular integral will be 0. Okay, so for the first equation, the auxiliary equation for the first equation f double dash x plus lambda into fx equal to 0, the auxiliary equation takes the form d square plus lambda equal to 0 if we denote capital D by d for d by dx. Okay, so d square plus lambda equal to 0, one equation, and the roots of the auxiliary equations are d equal to plus minus root lambda I. Similarly for second ordinary differential equation, the auxiliary equation, if we consider capital D equal to d by dt, the auxiliary equation will be d plus lambda alpha equal to 0, that is d equal to the root will be, there will be a single root minus alpha lambda. And so with plus minus root lambda I, the complementary function, and so the general solution is given by it is when lambda not equal to 0, their solution is fx equal to c1 sin root lambda x plus c2 cos root lambda x. Okay, you can compare the roots of the auxiliary equations. Here we have a pair of complex roots, and comparing it with alpha plus minus I beta, if alpha plus minus I beta is a pair of complex roots of the auxiliary equation, then the complementary function is given by e raised to alpha x into c1 cos beta x plus c2 sin beta x. Okay, and for the in second equation we have a single root minus lambda a, so considering that as a real root, we can write c e raised to minus lambda alpha t. Now we replace these expressions in the assumed solution. That is, the assumed solution is theta as product of fx and gt. Therefore, the solution of heat equation takes the form a sin root lambda x plus b cos root lambda x. That is solution of first ordinary equation obtained after separating the variables, and into the expression for gt, that is e raised to minus lambda alpha t. So this is the general solution of first one dimensional heat equation that is given here. Next is when lambda equal to 0, these both ordinary differential equations take the form f double s x equal to 0, that is d square operated on x equal to 0, where d is d by dx, and g dash t equal to 0, that is d by dt of gt equal to 0. So solution of first equation f double dash x equal to 0 is a0x plus b0 and gt equal to c0, where a0, b0, c0 are arbitrary constants. So with this fx and gt, our assumed solution now takes the form theta equal to a0x plus b0. We have merged the arbitrary constants and written them a0 and b0. So theta equal to a0x plus b0. So for the case lambda equal to 0, we have this solution, and for the case lambda not equal to 0, we have another solution. So we apply the principle of superposition, that the solution will be linear combination of these two, both of them, with the constants 1 1 we can consider without loss of generality. So here we add the both solutions in case of lambda equal to 0, lambda not equal to 0, and we get the solution by principle of superposition, that is theta equal to a0x plus b0 plus a sin root lambda x plus b cos root lambda x into e raised to minus lambda alpha t, where a0, b0, a, b and lambda have to be chosen to satisfy the boundary conditions. Now comes the boundary conditions. Now we use the boundary conditions to find these arbitrary constants. So the boundary conditions are these. If you need, please note them. Now one by one we use the boundary conditions, and we have values of a0, b0 equal to 0, the constant b0, constant capital B equal to 0, and the value of root lambda in terms of r, that is n pi by r, where n is integer. So with these arbitrary values of arbitrary constants, we write the solution, and that is of this form: theta equal to a into a0x plus b0 plus a sin root lambda x plus b cos root lambda x into e raised to minus lambda alpha t, and theta can be considered here as a sin n pi x by 2r into e raised to minus n pi 2r alpha t. Now the boundary condition, one boundary condition is not used here, that is theta equal to 1 at t equal to 0 and x greater than 0, and this must be satisfied. So let us see more general format of the solution by principle of superposition again. In the last solution, a is arbitrary constant, and for a we write ans, and then by superposition this takes the form summation n equal to 1 to infinity an sin n pi x by 2r e raised to minus n pi by 2r into alpha t. Okay. So comparing these, now we use the boundary condition theta equal to 1 at t equal to 0 when x greater than 0 in this solution, and we have 1 equal to summation an sin n pi x by 2r, n equal to 1 to infinity. So using this, we just integrate over the region 0 to 2r. We consider the continuous sum. So integral 0 to 2r sin m pi x by 2r dx, integral 0 to 2r sin m pi x by 2r, and summation over the right hand side is also there, but this is the continuous sum, and so integration and summation can be interchanged, and therefore we have this form. Now here sin m pi x by 2r and sin n pi x by 2r, they are orthogonal with respect to the weight function, that is unity, over the interval 0 to 2r when m is not equal to n. Okay. So in general, now what are orthogonal functions? So in general, if any two members of f and g of a set of functions satisfies the condition integral a to b fx dx dx equal to 0, then f and g are said to be orthogonal and is known as orthogonal condition in interval AB. So the orthogonality of two functions f and g also depends on the interval of integration. For example, 1 cos 2x sin 2x, this set is orthogonal set over the interval from minus pi to pi. So here we have used the concept of Fourier series to find the expression of ans, okay. And the representation of a function by means of infinite series of sine function is known as a Fourier sine series. In 1822, Fourier in his work on heat flow made a remarkable assertion that every function fx with period 2L can be represented by a trigonometric infinite series named after Fourier and Fourier series. Fourier series is known as essential tool for the analysis of all kinds of waveforms ranging from signal processing to quantum particle waves. The Fourier series expansion of a periodic function fx having period 2L is given by fx equal to a0 by 2 plus summation an cos n pi x by L plus bn sin n pi x by L, where a0, an, bn are called Euler formula and given by these three integrals. So in case of solving a partial differential equation, after getting the general solution by method of separation of variable, we may need to use Fourier series, half range Fourier series for finding the arbitrary constants and to get the solution of the given PDE at the end. Thank you.
SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.